Good evening, everyone. We're now going to kickstart the next presentation in track 1. Before we begin, a quick introduction of our speaker for this slot, Mr. Dino Daizovi. Dino Daizovi is an information security professional, researcher, and author. He has been working in information security for over 8 years with experience in red teaming and penetration testing at Sandia National Laboratories, at Stake, Bloomberg, and Matasano. He currently manages information security for a technology-based finance firm in New York City. As an independent researcher, he is a regular speaker at industry, academic, and hacker security conferences, including presentations of his research on hardware virtualization, assisted rootkits using Intel VTX, Takama Wireless Client Security Assessment Toolkit, and offensive security techniques and tools at Black Hat USA, Microsoft Blue Hat, Kensec West, the Usenix Workshop on Offensive Technology, and DEF CON. He's perhaps best known in the security and Mac communities for winning the first Pwn2Own contest at Kensec West 2007. And today he's talking about macOS exploitation. Join me in welcoming Dino Daizovi.
Thank you, everyone. This is my first time in Kuala Lumpur, and it's pretty awesome. So I had roti canai for the first time a couple nights ago. That's amazing stuff. I think I'm going to have it every night while I'm here. So I'm going to be talking about hacking Macs. So if any of you wanted to win the Open Hack competition, and you're sitting on a vulnerability, just had trouble getting the exploit to work, you've come to the right talk. If you don't have a vulnerability, well, there's couple hours the rest of the day, you can find one and you'll be fine. So why are we going to talk about Mac exploits? Macs are becoming way more prevalent, especially in consumer laptops. For instance, in the US, during July and August, 20% of the laptops sold in US retail were Mac laptops. And so especially in the last year, there's been an explosive growth in them. And just in various areas, like in New York City, where I live, there's almost everyone has a Mac laptop. It's kind of silly. You very rarely see someone with a PC and, at a coffee shop or something like that. And even here, you see a lot of people with Mac laptops. And because the operating system is very different, it's a good idea to take a look at how secure it is to various attacks like malware and all the other things that affect other platforms. And one of my concerns is that even though malware does not currently target Mac operating systems, there's no reason why it couldn't. Mac is significantly lacking in a lot of the defenses that other operating systems have, like ASLR, NX, stack and heap memory protections, and basically they need to step this up pretty quickly before it becomes a problem. And there's also this very big difference in perception about the security of Apple products. And the way I explain this is that there's a difference between safety and security. For instance, depending on where your house is, it may or may not be safe to leave your door unlocked. No matter what, it's always insecure. Someone can always walk in through the front door, but you may or may not do it. And surfing the web with Safari on a Mac is like leaving your door unlocked. You're just hoping that nothing bad happens because there's nothing stopping it. So I was reading Nico Weissman's blog. He works for Immunity. And he said to make your presentations more interesting, you should use lots of pictures. And so all of his presentations have these really awesome pictures of bugs. And so I'm going to use pictures of ferocious cats. So also with OS X, the last operating system was called, 10.4 was Tiger. So we're going to start with the Tiger. We're going to move on forward. So I'm primarily concerned with memory corruption vulnerabilities. This is the larger umbrella that describes many types of exploits, ranging from the simple buffer overflow to integer overflows, out-of-bounds array access, uninitialized memory use, just all this stuff that lets you corrupt memory and application state and ideally execute code. Other operating systems have discovered that, this is a huge problem. This is enabling web drive-by downloads, system compromises, and so there's a variety of defenses that have been shipped in other operating systems. I'm going to talk a little about in case anyone's not familiar with them. These are address space layout randomization, non-executable memory, and various stack and heap memory protections. I'm also going to talk about how OS X tries to do these, but it actually doesn't. They kind of try and get them as marketing bullet points, but they sort of fall flat in their actual implementation. So first off, address space layout randomization. Main idea here is that all memory corruption exploits, almost all of them, require hard-coded memory addresses. So these might be the return address that you use for a overwritten in a stack smash for the overwritten return address. Might be other things you use, overwritten pointers, various other things. All of them are hard-coded memory addresses. So ASLR just shuffles memory so that an attacker has no way of knowing what these are, or it's very difficult, so they have to guess. And basically, in guessing, they may crash the application if you only have one try before the application crashes and it doesn't restart itself. Or it'll just, at minimum, it'll stop a worm from spreading. Because if 1 out of 256 tries fails, worm's not going to get off the ground, but an attacker can just try it multiple times, and they may still succeed. This was pioneered by the PAX project for Linux, which is the first known implementation. And at this point, like for Linux, I'll just talk about Ubuntu. Ubuntu ships with full ASLR. It's randomized dynamically for each process, very solid. Windows Vista has full ASLR. It's randomized at system boot, so it's the same if you restart the process, and it's also the same for all processes on the system. Except for some elements of the address space are moved around a little more, like the stack and the heap. They have these little offsets that are purely random. But in particular, DLLs are at a fixed place. Leopard, it actually, for OS X Leopard, it's really not accurate to even say that they have ASLR. What they have, and even Apple admits this, is they have what's called library randomization. And what this does is this just shuffles the libraries on the system whenever the operating system or the applications are updated. So I'm going to talk a little bit more about how this works. So there's a command line tool called update DYLD shared caches. And the interesting thing to note about this is they did not implement this for security reasons. Basically, they had this for optimization. It's called library pre-binding. So instead of linking all your libraries when the process launches, which can be time-consuming if you have a lot of libraries that you depend on, what they'll do is they'll do what's called pre-binding. They'll just take a bunch of libraries, merge them all into one big image that are already linked together, and then in most cases just load that whole thing up. And just because it was essentially free, they decided to randomize this. Because they're gluing them into a big image anyway, it doesn't hurt to put them at random places. And so what this is this creates a shared region cache file that's stored on the file system, and this is basically loaded into every process at launch time, and then when the application needs to load a library, if it's already in there, it just uses the one in the cache. Otherwise, it actually loads the library and will do the linking and things it needs. So keep in mind that these are randomized, or these libraries that the application may use are randomized, but there are several important things that are not randomized. That includes the base address of the executable itself. Most importantly, the runtime linker, DYLD, is not randomized. It's always stored at the exact same place in memory. And it's what is used to link everything else, so you'd think you'd want to randomize that the most. A piece of memory called the COM page, which is a bit of code that is shared between the kernel and userland. Stack segments, heap memory, memory allocated with mmap. None of these are randomized. These are all at the exact same location. And so as I mentioned on the last slide, when the shared region cache is created, they actually store a map of this cache. And it's nice in a nice text-readable format, or human-readable text file, that you can just go through and see which libraries are loaded in there and where they're loaded in memory. So for instance, for a local vulnerability, you can just, you don't need to worry about randomization, one, because you can just look at it in one process and look at, see where libraries are loaded in one process. You know they'll be loaded in the same place in a target process. Or you can just read this file. So the next security feature that Apple kind of half does is non-executable memory. The main idea here is that code execution exploits are taking advantage of the fact that writable memory that's supposed to be data gets loaded with machine code, and the application gets tricked into executing it. Well, you should never be executing data bytes as code bytes. So the idea is it will mark data pages as non-executable to make sure that they aren't executed. And the reason you have to do this is special is that x86 processors prior to some Pentium 4s and the Intel cores didn't actually support non-executable memory. Pages were readable or writable. If you could read a page, you could execute code from it. And at the same, because of that, the PAX project, the same project that invented ASLR, they used a very creative technique to implement truly non-executable memory by desynchronizing the TLBs on an Intel processor, so that basically if you tried to access a page and page it in that was as data, they could detect that versus if it was tried to be paged in as text. And so this is implemented now in a variety of operating systems. Linux with PAX and JR security patches. Windows has DEP, which will do hardware DEP where it's supported on the processor, or software in other cases. OpenBSD has this as well. And the real implementation of this uses, as I mentioned, the NX bit that's supported in more recent processors. So the hardware is there, and it's on every processor that Apple ships, or every x86 processor that they now ship, but they barely use it. They just set the NX bit on stack segments. So at least they do it on the main thread stack and all the additional thread stacks, and that'll stop the most basic Stack Overflow, but really nothing else. It's actually really easy to get around. And so that's what we're going to do. So one of the things that I developed was just a very clean stub that you can take any Stack Overflow, and instead of just returning into, instead of just using a return address to return into a library, then back into your code, you can just paste this stub, and it will do all this, black magic to copy your executable payload to the heap and execute it from there. And the way it does this is it depends on three what I call non-features, three artifacts of how Apple does things. Like I mentioned before, their library randomization does not randomize DYLD. So DYLD is the shared linker. Same thing as shared linkers on other Unix operating systems. And it's been at the same start address since the beginning of OS X time. And one of the other things it does is so in Leopard, because all the libraries are randomized, any shared library functions they used to use, they can no longer call the libraries for. For instance, in Tiger, libsystem, which is like libc for OS X, but with like a bunch of other stuff thrown in there, used to always be at the same location also. So they would just link DYLD and libsystem together, and so they could call functions, in each other without really having to link, because the linker is the first one that's loaded. It can't link until it's done executing. So what they do in Leopard is they just basically paste in the implementation of several library functions into DYLD. And one of these is the function setJump. SetJump and longjump are used to basically save your executing context to the stack, and then you can resume it later on. It's for like a really long-range go-to. And so basically we're going to use that in our stub to kind of use it in a very tricky way to gain control. And the other thing we're going to use is the fact that Stack Overflows on x86 can use what's called return chaining. So it's basically like returning into libc multiple times. Instead of returning into just one function, because functions on x86 take their arguments from the stack that the attacker has completely overwritten, you can return to one function, and it's going to pop arguments off the stack from the overflown buffer. And so you can return to one function, and then another, and chain these all together to basically, essentially, write a program all through kind of backwards returning. So it's kind of tricky. And the return chaining, I kind of have this admittedly somewhat crappy diagram at the bottom of my